So last time I ended my first lecture in probability with the topic on the fundamental counting principles. So we have this thing called the fundamental counting principle, but we have other counting principles. We have two more. So all in all, we will talk about three counting principles. If an experiment has k phases or k stages, and there are n sub k possible outcomes for each phase, then the overall number of possible outcomes for the entire experiment is going to be, capital N is equal to n sub 1 times n sub 2 times n sub 3, so on and so forth until you get to n sub k. So this is just multiplication. You multiply the possible outcomes of each stage of your experiment. Now, not all books write the fundamental counting principle that way. They don't describe it that way. Some other books use events instead of outcomes. So given k groups where each group has n sub k events. N sub k events is the number of events in the stage of your experiment. The total number of combinations of events for the entire group or for all group is this, n sub 1 times n sub 2, so on and so forth, times n sub k. So let's say you entered a coffee shop and you are interested in getting some snacks. The coffee shop offers 3 types of coffees and 4 pastries. In how many ways can a customer, such as yourself, choose your snacks if you were to order only 1 coffee and 1 pastry? Okay, so this is like an experiment that is composed of 2 stages. In the first stage, you will choose what coffee to order. And you have 3 possible choices. And so, the outcomes for the first stage of the experiment is 3. That is your n sub 1. And then after that, you will choose from the list of pastries. And there are 4 possible outcomes for your choice. And so n sub 2 is equal to 4. So the total number of possible combinations or outcomes for this experiment is n sub 1 times n sub 2 or 3 times 4, which is equal to 12. So you can visualize this thing, the fundamental counting principle, using a tree diagram. So in the first stage of your experiment, you will choose from 3 coffee. And these are the possible outcomes. You can choose Cafe Americano, Cafe Latte, or Cafe Barako. And after that, you will choose what pastry to go along with your coffee. And for each coffee, you have 4 possible choices. Apple pie, Banberry cake, bizcocho, cinnamon roll. The same with Cafe Latte. Apple pie, Banberry cake, bizcocho, and cinnamon roll. And so, the total possible outcomes in this experiment, the possible combinations of coffee and pastries that can arise from this experiment is going to be this, Cafe Americano and then apple pie, Cafe Americano, then Banberry cake, Cafe Americano, and bizcocho. So how many outcomes in all? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So this is the experiment. You will roll a die, a fair die, and then you will draw 1 card from a deck of 52 cards. These are the usual classic examples when we are introducing the fundamental counting principle. What is the total number of outcomes? So when you roll a die, how many possible outcomes can arise from that experiment? There are 6. 1, 2, 3, 4, 5, 6. And how about when you draw a card from a deck of 52 cards? There are 52 possible outcomes or 52 possible events. So all in all, the total number of outcomes for this experiment is 6 times 52, which is equal to 312. So this is the second counting principle. You have the fundamental counting principle, you have the permutation, and actually the third one is combination. So what is permutation? The permutation of a set refers to the number of ways the elements of a set can be ordered or arranged. So let's say, for example, this is your set. You have 3 elements. Let us list down all possible arrangements, okay? Ordered arrangements of the elements of the set. We can write it as ABC, ACB, CAB, BAC, BCA, or CBA. All in all, you have 1, 2, 3, 4, 5, and 6. We can also apply here the fundamental counting principle. Okay? We will produce a list of arrangement for the elements of the set. So in the first stage of the experiment, you will choose which letter to write down first. And for that, you have 3 choices, 3 possible outcomes. So n sub 1 is equal to 3. Now, when you go to the next stage of the experiment, which is writing down or choosing the second letter, you no longer have 3 possible choices because you already chose 1. Okay, you already wrote it in the first letter. And so you are only left now with 2 possible outcomes or 2 possible choices. And in the third stage of your experiment, you will choose the last letter. And since you have chosen already the first other 2 or the other 2 letters, you are left only with 1 letter in the last stage of your experiment. And so using your fundamental counting principle here, the total number of possible outcomes or ordered arrangement of a set that has 3 elements is going to be 3 times 2 times 1, which is equal to 6. Given a set S, how many permutations of objects will arise if you will choose only 2 objects from set S? Okay? Again, in the first stage of the experiment, you will write down the first letter and you have 3 possible choices there, 3 possible outcomes, and so n sub 1 is equal to 3. Now, when you go to the second letter, you are left with only 2 elements. And so that is going to be n sub 2 is equal to 2. So again, using your fundamental counting principle, the total number of permutations of objects, if you will choose only 2 objects from set S, is going to be 3 times 2, which is equal to 6. So you have a permutation formula. Okay, so lucky for you, this is not the first time you are seeing this. This is part of junior high school and part of senior high school statistics and probability. And permutation k, that is how you read it. And permutation k is equal to n factorial divided by n minus k factorial, where n factorial is this, n times n minus 1 times n minus 2, so on and so forth. But I personally prefer to write it in this way. N factorial is equal to this, 1 times 2 times 3, so on and so forth until you get to n. These are the other notations for the permutation formula. N permutation R or N permutation K. So let's say, for example, I have set S with 6 elements. How many permutations of 2 objects can you produce from set S? Well, this is the formula. It's N permutation K. N is the size of your set, the total number of elements of the set. And K here is the objects that you will choose. Okay, the number of objects that you will choose from set S. 2. Okay, so 6 permutation 2 is equal to 6 factorial divided by 6 minus 2 factorial. And 6 minus 2 factorial is 4 factorial. You can write it in this way, okay? But pay attention to this. 4 times 3 times 2 times 1, that is just 4 factorial. That is just 4 factorial. And this one is just 4 factorial. This is multiplication. And so 4 factorial divided by 4 factorial is equal to 1. And so you are left with 6 times 5, which is equal to 30.